Okay, guys, we are continuing on with Euclidean geometry. Hello. This is your favorite host, Maths is a Game. We are, I guess we are on another mission to actually uncover, not just cover, but uncover the something. We are going to do something. Euclidean geometry. Okay, we are obviously now today we are going to be looking at circle geometry, because what we have done in previous lessons is we looked at just like the beginnings of geometry, and by that I say we looked at lines, we looked at angles, we looked at triangles, we looked at parallel lines, we looked at the combination of scenarios around those concepts. So today, as promised, we are going to look at Euclidean geometry. Specifically, we are going to venture into circle geometry. Now, I just want to say from the get-go that circle geometry is a grade 11 relevant topic. So here, guys, we are obviously capping it off. My grade 11s will be benefited to be here. All right, let me just for a second just share this with I thought I should just share that with my grade 11s because I don't want to leave them out of the thing, you know. Please let me know in the comment section if like you guys are experiencing any like network or lags in the live. Let me know immediately, please. Be kind enough to let me know immediately the moment you do sense that the live lesson is basically lagging or for some reason glitching, so that I can be able to see how I can best fix that, hopefully immediately. Okay, so let's jump right into it. Firstly, it would be important to first lay the foundation by talking about the different parts of a circle, but also firstly defining what is a circle. Okay, so let's first define what a circle is. What is a circle? A circle is a set of points. What about these set of points? Well, these set of points are equidistant. Now, the word equidistance has to do with the set of points being of equal distance. But equidistance from what? Well, they are equidistant from a fixed point called the center. So that's very important to first set us off in our basic understanding of circle geometry. Circle geometry is not going to make sense until we understand that what is a circle. A circle is a set of points. Set of points that are equidistant. They are equidistant from a fixed point which we refer to as the center. That's what a circle is, guys. Okay, a circle is a set of points that are equidistant from a fixed point called the center. So if anyone ever asks you guys what a circle is, now you know that a circle is a set of points that are equidistant from a fixed point which we call the center. Okay, all right. So I know this may not necessarily be the most perfect circle that you've ever seen, but you know what, guys? It accomplishes the purpose, doesn't it? All right. Yeah. Then what we would have there, smack bang, is that fixed point that we call the center. But a circle in of itself is a set. So what makes the circle is a set of points, and these points, they are all of equal distance from the center, which is the fixed point. Okay, that's very important to note. Okay, so we call these guys the center. We call this the circumference. Okay, so the center is obviously that fixed point, right? It is that fixed point by which we have a set of points that are equidistant from that fixed point. That's the center. Then the circumference of the circle in the situation is what we call the distance. It's the distance around the edge of a circle. The what? The distance around the edge of the circle. We call that the circumference. So this is the center, the fixed point. Then this is the circumference, the distance around. Okay. I'm sure when you guys did area and perimeter, you'll remember that when you did the perimeter, which is the distance around the circle, which we refer to as the circumference, the formula for circumference for a circle is 2 pi r. That is the formula for calculating the circumference around the circle. Then a line from the fixed point, the center, to the circumference, we refer to that. Let's see if people can tell me. We refer to the line from the center to the circumference as what, guys? What do we call that line? Come on, help me out. I know you know. The line from the center to the circumference is called the, thank you Molimo, the radius. The radius. Okay. Line from center to any point basically on the circumference. To any point on the circumference. That is the radius. Okay. Okay. Then we have this line. A line basically that comes from one point of the circumference all the way to a other point of the circumference, a line that connects one end of the circumference to the other. What do we call that line? What do we refer to that line as? A line that comes from one end of the circumference to another. It seems like Molimo is like the go-to person here. Molimo is the GOAT. Gazi, thank you so much for coming in and actually putting in your contribution. So we call that a chord. Okay. Okay. A chord is basically a line from one end of circumference to another. Okay. And what a circumference does, it actually divides. What does it do? It divides the circle into what we call segments. All right. So for instance, this here, this region now that you see here, okay, this area we would call, because like I said, what a chord does is it divides our circle into segments. So we would call this a minor segment. Why do we call this a minor segment? It's a very small segment of the circle. Then this other side, which is like bigger, the bigger area, we would call a major segment. So what a chord does, it divides the circle into segments. That's what a chord does. Divides the circle into, in fact, this chord divides the circle into how many segments? We have this minor segment, and then we have this big major segment. So we'd call this the minor segment, whereas we'd call this the major segment. Okay, very important words, a segment. Okay, a segment. Okay, continuing right along. Then there is that line that passes through the center, goes to the other side of the circumference of the circle. It's kind of like a chord, but it is a special kind of chord, but because it passes through the center. So it's a special kind of chord. What do we refer to that chord as? It's got a special name. It cuts through the center from one end of the circumference to the other. What do we call that special chord? Okay, we refer to that special chord. Yes, Benzo, very good. Molingo, very good. Lupumzo, very good. We call that special chord a diameter. Okay. So I really literally say it's a special chord. Yes, it is a chord, but it's a special kind of chord, because what basically does it do? It passes through the center. So it passes the center. Okay, it passes the center. It is twice the radius. That's another thing that we need to note. It is twice the radius. Okay, and it is the longest chord that we have in a circle. The longest chord. Maybe those are properties you guys might have not been aware of. Okay, so a diameter is a line that extends from one end of the circumference through the center to the other end of the circumference. So it's a special kind of chord. But what do we know additionally? It passes through the center. Passes the center. It has to definitely pass through the center, because that's what makes it unique. It is twice the radius. So the radius is half the diameter, whereas the diameter is twice the radius. Very important. And also, the diameter is the longest chord that we actually have in a circle. All right. Hey, I hope we are catching stuff here, and it's nice catching that we are having, and it's good. Okay, longest, yes, the longest chord. Yeah, okay. Then, all right, in all these things that we are learning, all right, and we are understanding, we also have, of course, when the diameter is there, we know that it divides the circle into two halves. So there is a semicircle that arises because of the diameter. Two semicircles, right? Two semicircles that basically form equal segments, if you want to call it that as well. Two semicircles, a semicircle. Okay. Then let's continue. We also now have something that we refer to the part or a part of the circumference. A part of the circumference. Let's say we had A here and we had B there. Okay, we call AB a what, guys? What do we call AB? Okay, because AB would just be a part of this entire circumference. So a part of the entire circumference, what do we call a part or a portion of the circumference? What is the name that we ascribe to AB? What do we call that? Yes, Molimo, Ontatile, very good. Okay, just be mindful of the spelling. It's ARC, arc. Okay, what is the arc? A part or a portion of a circumference. We call that a arc. So for instance, AB is an arc. If let's say we had C, look at BC would also be what we call a what? A arc. Okay. C, let's say we had D as a point here. CD is an arc. D, let's say we had F here. DF is an arc. All right. So an arc is a part or a portion of our circumference. We refer to that as a arc. All right. Hope we are clear there. Hope we are clear there. Hope we are clear here. I just want to draw a separate circle here because I want to emphasize a point right now of another important line that we need not forget. A line that touches the circle at a point, but it is external to the circle. I wanna emphasize that one. A line. Okay. All right. What is it called? A line touching the circle at a point, but this line is external to the circumference, excepting at the point where it touches. What do we call that line? What do we call that line? Very good, guys. We call that line a tangent. Tangent. A tangent is a line that simply touches the circle at a point. Okay? It simply touches the circle at a point, but please, guys, the tangent is external to the circle. It is external completely, but excepting at the point where it touches. Okay? That's basically what we mean by it being a tangent, because it simply touches at one point. Now, someone in the comment section, I don't know if Carla Zokot is basically maybe trying to be funny or something like that, but I did say from the get-go, let us show forth a little bit of mercy when it comes to the drawings, okay? Because I did not claim perfection in the drawings, not even. So if you guys are going to become critical about the drawings, that it stands in the way of you learning, then I guess, guys, yeah, that's your baby. But for me, as I'm saying, I'm just trying to explain the concepts. Hopefully you guys get the point. Okay, now with that said, I want to ask you guys, okay, what else do you guys want to share with us insofar as the circle itself? Okay, there's one more thing that's coming to my mind right now. A line that cuts through the circle basically does not stay within or stay at the end points of the circumference within the circle, but extends beyond. What do we call that line? Yes, Gaziti. We call that a secant. Okay, a secant. All right. Yeah, it basically has no it behaves a little bit irrationally than a chord, because instead of it staying inbound at the end of the circumference and staying within, it just decides to extend beyond that. Okay. What do we call a pizza slice? What do we call the pizza slice? The pizza slice is referred to what? Yes, on Tatile. A secant cuts the circumference of the circle at 2 points, and it extends beyond the circumference of the circle. What do we call a pizza slice, guys, of a circle? This would be, if you had ordered Debonaise, or guys, I love Roman's pizza. Roman's pizza, like, literally I think is the best pizza in the country, I'm sure in the continent, in the world. So if you had a pizza slice from Romans, what do we call that pizza slice in Euclidean geometry? Because we mentioned was that this is a minor segment, then this bigger part would be a major segment. But what do we call a pizza slice in geometry? We call it starts with the S. We call it a what, guys? We call it a sector. Okay. Yeah, key pizza slice. The area of the pizza slice is referred to as a sector, not a segment. A sector. Okay. Yeah. This one, chord, right? We call this a segment, but this one we call, the pizza slice, we call a sector. All right. Okay. So guys, once we have a pretty good grasp and understanding of these things, what a center is, what a radius is, what a chord is, what a diameter is, what a circumference is, what a minor and a major segment is, what a sector is, what a tangent is, what a secant is, what a arc of a circle is. When we understand these things, it lays a very good foundation so that we can build on that knowledge into the individual theorems that you guys then get to learn in grade 11. So it's important to understand the basics. What is a circle? We said a circle is a set of points that are equidistant from a fixed point called the center. The center is smack bang there. Okay. So all of the points that make up the circumference that are connected, they are points that basically that are continuous, that join to form a circle. But these points are equidistant from the center. The radius is a line from the center to the circumference. The diameter is a line that passes through the center from one end of the circumference to another. The chord is a line that extends from one end of the circumference to another, does not pass through or necessarily pass through the center. It doesn't have to, okay? Because our diameter is a special kind of chord. It is twice the radius and it is the longest chord. That's the diameter, you see. minor segment. We understand what a minor segment is. A chord divides our circle into two segments, a minor segment and a major segment. Major meaning bigger, minor meaning smaller. Then we have what? A arc. We know what an arc is. Okay. Tangent. We know what a tangent is. Secant. Secant is pretty much straightforward, and we know what that is. Now, I just want to mention one last thing. When a circle has a four-sided shape, right? And these points of the four-sided shape all touch the circumference of the circle. In other words, we call this a cyclic quadrilateral. When a circle has a four-sided shape that basically has all its points lying at the circumference of the circle, we say that this here is a cyclic quadrilateral. Okay, it has all the what? All the vertices on the circumference. All the what? The vertices. By vertice, vertex is the point that forms a angle. We spoke about that. This is a vertex. Two lines where they meet, we call this a vertex. Two lines where they meet, we call this a vertex. Two lines where they meet, we call this a vertex. Vertex is singular, one vertex. Vertices is plural, many vertices. So A, D, C, and B are your vertices. Obviously, vertices then form angles, right? That we understand. Okay, that they use, which is concyclic. Concyclic is synonymous to cyclic quadrilateral. So the minute they say concyclic, that has to do with the fact that vertices are found on the circumference of the circle, four-sided shape that you probably have formed, and therefore we call that a cyclic quad. Another word that is used very popularly is concyclic. The minute you hear the word concyclic, you know about, okay, is cyclic quad this thing, all right? Okay, so guys, this is just the basic foundational work. Anachi Maseti, thank you so much for the roses. Really appreciate them. I saw those roses, 1, 2, 3 of them. Thank you so much, my dear. Really appreciate you and showing the love. As I said, guys, the minute you experience some sort of like glitch in the live, please do let me know so that I can try and fix the situation if it is feasible to do so from my side. Now, guys, having established the basic understanding of circle concepts, we can now dive into the actual meat of the day when it comes to geometry in grade 11. Okay. Yeah, because they are what we call the Center Theorems, and they are divided into four groups. We are going to look at those four groups. As benzo. Okay, sorry guys, I didn't let me zoom out. I'm sorry though, the quality, guys. Hey, you will have to excuse me for the quality. You see, quality of the thing I'm about, maybe it's not the best. Hey. Yeah, work in progress, guys. We'll get there, ne? We'll get where we need to get. Just be patient with otherwise one day is one day. We'll get where we need to get. All right. But yes, guys, this basically is just maybe a nice little brief summary, and maybe let's also do the following for you, because it says writing may not be the best. So we are going to say thank you to Jen. Okay, there's currently a program called Jen that is running very successfully across the country with many valid, beautiful programs there in Jen. So maybe the Jen notes as well will help us out so that we can see the English language very well and the representation of things as they ought to be. Yes, there are things that I added in my diagram, okay, just so that we can have a fuller understanding and knowledge. But okay, of course, this also summarizes what I've just explained to you guys very nicely, so that you can also just have that brief, short notes, so that you can also recap for yourself your own time. Okay. Molimo is like, where can we get these notes? Just send me your if you can send me your contact details or email address. I will email you the notes if you need them. Okay, all right. Yeah, let me be generous. Let me not hold back to you guys. This is for you. At the end of the day, you are the ones that need to do the things. All right. Okay, let's move on, guys. Circle theorems. Okay. So now we have what we call circle theorems. And these circle theorems, we are going to divide them into 4 groups. All right. Yeah. So there are those theorems. Yes. Send me the info. I'll send you guys. So there are theorems that have to do with what we call the center. We call them the center theorems. Theorems that have to do with the center. The key word is the center. And we already know what the center is. It's that fixed point by which all set of points equidistant to that point basically then form what we call the circle. Okay. Yeah, the radius is able to emerge from there. The diameter is also passing through there. You see, so we look at the center theorems. So guys, here is the first theorem statement. Please take note what the first theorem statement says. The first theorem statement says the line drawn from the center of the circle perpendicular to the chord, perpendicular. So the line drawn from the center of the circle perpendicular to the chord. What does it do? It bisects the chord. Let's look at this again. The line drawn from the center of the what? Of the circle perpendicular to the chord bisects the chord. So what we can see diagrammatically from what we are reading is that there's this circle. The center is there. There is a line drawn from the center. The line drawn from the center. Here it is. You have the center here. You have a line drawn from the center. What do we further learn? The line drawn from the center of the circle perpendicular to the chord. So that means we have a chord then. And guys, this is a chord because we know what a chord is. From one end of the circumference to the other, that's definitely a chord. So a line drawn from the center of the circle perpendicular. So there is our box for right angle 90 degrees. Line drawn from the center of the circle perpendicular to the chord. So this is what you would see in your diagram. But what are they concluding about a line drawn from the center perpendicular to the chord? We know that it bisects the chord. So in other words, if, let's say this is A, M, B, O. In other words, they are saying if OM is perpendicular to AB, but guys, given that this OM is a line from the center perpendicular to the chord, so if OM is perpendicular to AB, then what is the outcome? The outcome is that AM is equal to MB. AM is equal to MB. If OM is perpendicular to AB, then AM is equal to MB. Now guys, if I'm given a diagram like this, my statement that I would be able to write is the following. This is the statement I would be able to write. I would be able to say AM is equal to MB. That's my statement. My reason for saying AM is equal to MB, which is an acceptable reason, is for this theorem, line from center perpendicular to chord. Let me repeat this again. What do you see in the diagram? You see OM is perpendicular to AB. What do you write as your statement? You write the conclusion that you can make based on the diagram. What is the conclusion? If line from the center is perpendicular to the chord, we know that the line actually does what? It bisects the chord. This here you don't see in the diagram, but here, this one, you see. You see this? You don't see this in the diagram. In the diagram, what you see is OM being perpendicular to AB. What you don't see is AM being equal to MB. So your statement is something that you don't see, but your reason is what you see in the diagram. This is what you see. Line from center. There we go. Line from the center perpendicular to chord. Perpendicular to chord. Your reason is seen. Your statement is unseen. Okay, so let's go and read the theorem statement once again. The line drawn from the center, which line? Here is the line. It's OM. It's drawn from O, which is the center, and the line drawn from the center of the circle perpendicular. What does perpendicular mean? Look at this line. It's making an angle of 90 degrees with the what? With the line AB. So the line from the center perpendicular to the chord. What does the line from the center perpendicular to the chord do? What does it do? The line drawn from the center of the circle perpendicular to the chord bisects the chord. So what I'm saying is, based on this diagram, what do you see? A line from the center perpendicular to the chord. What you see is OM is perpendicular to AB. What can you conclude which you don't see in the diagram? You can conclude that AM is equal to MB. Why? Because of the line from the center perpendicular to the chord. So the statement, as I said, is something you don't see in the diagram. AM being equal to MB is not explicitly given to you in the diagram. It's something that you don't see. It's something that you have concluded. It's come from the if part. Then, voila, magics. AM is equal to MB. So AM is equal to MB is unseen. We can conclude that based on the OM being perpendicular to AB. So we say AM is equal to MB. What's the reason? The reason is seen. The line, which is the line from the center, there is the center, is perpendicular, look at the 90 degrees, to the chord. Look at AB, it is the chord. So this is the seen reason and the unseen statement. That is coming from theorem number 1. Okay. Now I know someone like Wahab Ottos was saying, come again, say that again. Please repeat the way you give reasons. Dimpled, are you with me? Dimpled, are you with me? Okay. That's theorem statement number 1. The line drawn from the center of the circle perpendicular to the chord, what does it do? The conclusion is that it bisects the chord. What does the word bisect mean? It means that this line cuts AB into half. Bisect, bi means two. Sect is sort of like cut through. How do we cut? We cut into two halves, equal halves. So that's why we say AM is equal to MB. That is the conclusion based on this reason. AM is equal to MB. Why? The line from the center perpendicular to the chord does exactly this. The line from the center perpendicular to the chord does this. Okay. All right. So that is theorem 1, or that is one of the theorems that has to do with the center. So you need to know this theorem statement off by heart. Why? Because sometimes they ask you, they will write down the theorem statement and leave certain words out. You need to be able to complete and fill in the missing word. So the theorem statement is something you need to know off by heart. The line drawn from the center of the circle perpendicular to the chord bisects the chord. The line drawn from the center of the circle perpendicular to the chord bisects the chord. That's the theorem, one of our theorems that has to do with the center. Moving right along, here's the second center theorem. The line segment joining the center of the circle to the midpoint of a chord is perpendicular to the chord. Is what? Is perpendicular to the chord. So let's look at this statement one more time. The what? The line segment. Doing what? Joining what? Joining the center of the circle to the midpoint. The line segment joining the center of the circle to the midpoint. So let's see what we are referring to here. Here's our circle. There is the center. And what they are saying, the line segment. So there's a line segment, guys. A line segment is a portion of a line. It is not a line, but it's a portion. It has a beginning and an end. That's what a line segment is. So the line segment joining the center of the circle to the midpoint of a chord. So that means we have a chord again. But do you know what this time round? They are saying the line segment joining the center of the circle to where? To the midpoint of a chord. So let's say we have chord what? Chord AB, that is center O. So a line basically from the center that is drawn to the midpoint of a chord. What does it do? Is what? Is perpendicular to the chord. Is what? Is perpendicular to the chord. This theorem is obviously the reverse of the previous theorem statement. The line segment doing what? Joining what? The center to the what? To the mid. So this is the chord midway in the middle of that chord. The line segment joining the center of the circle to the midpoint of a chord. So this is like the chord and this is like midway. Hence you have this and that being equal. So in other words, this time round they are saying if AM is equal to MB. Do you see that this time round the if part has changed? If AM is equal to MB, then what can we conclude, guys? If AM is equal to MB, according to this statement, what are they saying? The line segment joining the center of the circle to the midpoint of a chord is what? Is what? Is perpendicular to the chord. So what can we conclude? If AM is equal to MB, which is what we are given this time round, that's what we see. What is it that we do not see? What do we conclude as per the conclusion of the statement? If this is true, then what is the conclusion? The midpoint is the line from the center to the midpoint would then be perpendicular to the chord. So if AM is equal to MB, then what? Then we know OM is perpendicular to AB. All right. So if AM is equal to MB, then OM is perpendicular to AB. Does that make sense, guys? Okay. So in our statement, what would be the statement for this diagram? OM is perpendicular to AB. OM is perpendicular to AB. Can you see that? Is the statement something that you see? No, you don't see that in the diagram. The fact that you are saying OM is perpendicular to AB, there is a solid reason why you are saying that. It's based on this theorem statement. OM is perpendicular to AB. Why? Here is the acceptable reason. Line from center to midpoint of chord. It's as simple as that. Line from center to midpoint of chord. So my beloved grade 11s, these theorems are very, very important. The center theorems, theorems that have to do with the center. Okay. Hey, I hope we are good here. Okay. Yeah, I hope we are good here. Okay. Can I move on? Are we good? can I summarize the theorem to short terms? This theorem, okay, in other words, this theorem is saying the line from the center to the midpoint of the chord bisects the chord. Do you hear that? The line from, the line from the center, that was wrong what I said initially. The line from the center to the midpoint of the chord is perpendicular to the chord. That's what I was supposed to say. The line from the center to the midpoint of a chord is perpendicular to the chord. The line from the center to the midpoint of the chord is perpendicular to the chord. You can see the if part of what I'm saying. The line from the center to the midpoint of the chord. What does the line from the center to the midpoint of the chord mean? It means AM is equal to MB. All of that language in English that I'm saying, the line from the center to the midpoint of the chord simply means AM is equal to MB. If that is the case, if AM is equal to MB, what then can I conclude? The line from the center to the midpoint of the chord is what? Is perpendicular to the chord. Then OM is perpendicular to AB. In other words, we can say angle OMB is 90 degrees and angle OMA is 90 degrees. Okay, you got it, ne? Very good. So please, guys, this theorem statement simply means that your statement you do not see, your reason is there in the diagram. Line from center to midpoint. This part, midpoint, makes this AM equal to MB real. Line from center to midpoint of chord. Okay. All right. Let's move steadily along to the next center theorem. So this is a theorem that has to deal with the center. Now, the next theorem takes on three important circles. Okay, we call this one, and I'm going to just write the statement: the angle which an arc of a circle, the angle which an arc of a circle subtends, and I'm going to unpack the language, don't worry, subtends at the center of the circle is twice the angle it subtends at the circumference of the circle. Okay, so let's unpack this one at a time. The angle which an arc. So let me draw one of the diagrams that represents this theorem. We call this, guys, an arrowhead. You know how let me just kind of, when I say it's an arrowhead, think about that's an arrowhead. So they have an arrowhead which is written or drawn inside the circle. Its vertices touch the circumference at 1, 2, 3 points, just 3 points only. Okay, all of these diagrams that I'm going to actually draw here have vertices only at 3 points. Okay, then the fourth point is not at the circumference, but it is at the center. Please take note of this. Okay, right. So what we are saying is the angle which an arc, guys, do you still remember what an arc is? We said, for instance, an arc is a part or a portion of a circumference. And we mentioned that from A to B, for instance, this is arc, we could call this arc AB. From B all the way to C, we could say that is arc BC. From C to D, we could say that is arc CD. From D to F, we would call this arc DF. So an arc is a part or a portion of the circumference. So what are they saying here? The angle which an arc of a circle subtends. Now listen to me and listen to me well. Here, let's say that is A, that vertex is A, let's say that is B, and let's say that is C. Let's say this is O and this is O1. BC is an arc, CA is an arc, AB is an arc. But here is the thing. They are saying the angle which an arc of a circle subtends at the center. So arc AC is not directly opposite the center. So we're not talking about arc AC. Arc AB is not directly opposite the center. But arc BC is directly opposite to the center. Arc who? Arc BC is directly opposite. So the word subtends has to do with directly opposite the arc should be the center. Arc BC is the only arc which is directly opposite the angle. So we say arc BC subtends. Do you see from C? You move in the direction, there's the angle. You move in that direction, there is the angle. So arc BC subtends the angle at the center because it is directly looking at opposite the center. So when they say the angle which an arc of a circle, they're not talking about this arc CA or AC. They're not talking about arc AB. They are talking about one and only one arc, and that's arc BC. I want you to note that the angle which an arc of a circle subtends. So this word subtend just has to do with directly opposite. Okay, the angle directly opposite the arc. All right, then let's continue. The angle which an arc of a circle subtends at the center of the circle, okay, is what? Is twice. What does twice mean? Twice means 2 times. It's twice the angle it subtends. Where? At the circumference of the circle. Guys, arc BC is directly opposite angle O. But you know arc BC is directly opposite angle A there at the circumference. It's directly pointing. You see B and C. You can put your 2 fingers there. When you move, they go directly to A. So BC subtends an angle at the center, which is angle O1. But BC simultaneously subtends an angle at the circumference, which is A. Now we are being exposed to a relationship that exists between the angle subtended by arc BC and the same angle that is subtended by arc BC at the circumference. What are they saying about those 2 angles? They are saying, listen, the angle which an arc of a circle subtends at the center of the circle is twice the angle it subtends at the circumference. So I want to ask you guys, if this is my arc, if this is my diagram, it's an arrowhead. I confirm 1, 2, 3 points, they are all at the circumference. This is my center. The angle here is 50 degrees. That is x. I want to know what the angle at the circumference is. Based on this theorem, what would be the value of angle A if the angle at the center is 50 degrees? Look at you guys rush to answer the question. Anati is like 25, Molemo is 25, Ontatile is 25, I Love Lab is like 25, Charlotte Doreen is like 25. So you guys are sure it's not 100. You are very sure it's 25, not 100. Okay, you guys are 100% sure it's 25, it's not 100. I'm just checking. But co-final, they always ask difficult, challenging. Why do they do this? Tando Malinga, of course, we are going to get to that difficult, complicated. I need you guys to first understand the concept. Okay. So Anati Maseti is like, we are sure it's 25. Guys, I would hope that you know that angle A, which is x, is definitely 25 degrees. When you write your reason, angle at center is equal to 2 times angle at circumference. Okay. Angle A is equal to 25 degrees. Let's read the statement again. The angle which an arc of a circle subtends at the center. So this angle is actually twice, which angle? It's twice the angle it subtends at the circumference. So the angle at the center is 2 times the angle at the circumference. In order for this angle to exist, you take this one, you multiply that angle by 2 to get that one. So you divide this one by 2 to get that one. Because multiplying this one gives me this one. Multiplying this one by 2 gives me this one. Dividing this one by 2 gives me that one. So let's never confuse that. I often find learners confusing angle at the center is twice the angle at the circumference as far as getting this specific numerical angle. So I hope we are all in the same page that it would definitely have to be 25. So guys, this is one of the diagrams, the arrowhead diagram. Another diagram that speaks the very same theorem is what I call shine bright like a diamond. 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 Look at this diamond. 1, 2, 3 points are all at the circumference. The 4th point is at the center. Okay. A, B, C. Which arc? This arc. Arc BC, directly opposite to the angle at the center, which is situated exactly there. All right. The angle that arc BC subtends is this angle. The same arc BC subtends this angle at the circumference. All right. So if that is O, angle BOC, the reflex angle, all right, will be equal to twice the angle at the circumference there. I repeat, angle BOC, this OC, the reflex angle, will be twice the angle there at the circumference. This is another diagram. It's not the arrowhead now. It is the shine bright like a diamond. Okay, I usually call this the diamond. All right, because A, B, C, 3 points, vertices at the circumference, 1 is at the center. Just like here, 1, 2, 3 points at the vertices at the circumference, 1 is at the center. The last and final expression of the theorem that I'm talking about is basically the bow tie. Mr. Bowtie. Okay. Mr. Bowtie, this here is usually the center. Okay. The bow tie, guys, center. There is the center. Mr. Bowtie. Hey guys. Yo. A, B, C. How many points, vertices at the circumference? 1, 2, 3. 1 is at the center. Bow tie, guys. The bow tie as well. The bow tie where one of the vertices is at the center. So arc, which arc? Arc BC, guys, subtends this entire angle here at the center. BC subtends this angle at the center. And arc BC subtends this angle at the center. The same arc BC subtends angle A at the circumference. So this angle BOC, is equal to 2 times angle A. These 3 are the 3 diagrams that represent angle at the center is 2 times the angle at the circumference. Knowing these 3 diagrams also helps you to confidently navigate a diagram that has many lines and the chords and so forth. Because when you can see these 3, then you will be fine. If you can see the 3. Okay, I usually say to my learners that think about a friend that you know very well. Okay, think about a friend that you know very well. If you have a friend that you know very well, do you know that that friend you can actually see? You can see that friend even if there are 100,000 people in a crowd. If you are given an elevated platform to stand and look into the crowd, if you know your friend very well, I'm telling you, if you're given binoculars and you are given a chance to actually pierce through the crowd, you will be able to see your friend in the crowd. These guys are your friends. You need to know how they look like. So for instance, angle at the center is 2 times the angle at the circumference is represented by these 3 diagrams. This is the first one, the arrowhead. The second one, shine bright like a diamond. And the third one, Mr. Bowtie. What do you notice about all of them? A, B, C. You have 3 vertices that are at the circumference. 1 is at the center. A, B, C. 3 vertices at the circumference. 1 is at the center. A, B, C. 3 vertices at the circumference. 1 is at the center. Are we together? So if you know then the theorem says the angle which an arc of a circle subtends at the center of the circle is twice the angle it subtends at the circumference. So you look at Mr. First diagram. Here is arc BC. Arc BC subtends this angle at the center. The same arc BC subtends angle A at the circumference. What is the relationship between angle O here and angle A there? This angle is twice the angle at the circumference. So if that is 50, that is obviously 25 degrees. And our reason is angle at the center is equal to 2 times the angle at the circumference. Let's say we used Mr. Shine Bright like a diamond. Shine bright like a diamond. You're a shooting star, I see, a vision of ecstasy. like diamond in the sky. All right. Let's say we had NPC. Let's say that's O. The O is the center there. Let's say that is 80 degrees. And then this angle here, we ask the question. They say find the value of this angle X. All right. So PNCO, right, gives me that 1, 2, 3 points at the circumference of the circle. My fourth is at the center. All right. So what I can do in geometry, as I always do, you turn your circle around, because you do these things, guys, so that you can see the diagram that you are accompanied or acquainted to. So PNOC, all right, if that is 80 degrees, this is a arc. The arc subtends this angle at the center. The same arc subtends which angle at the circumference? Angle N. So we know that this is one of your center theorems. Angle at the center here is going to be twice the angle at the circumference. Arc PC is what you have there. Okay. And then obviously arc PC subtends this angle at the center, but it also subtends that angle at the circumference. Based on this theorem that we've just learned, we learned that the angle which an arc of a circle subtends at the center, okay, is twice the angle it subtends at the circumference. So if that is 80 degrees, what is the value of this angle X here? Charlotte, 160, right? Very good. 160. Okay. So it's as simple as that, guys. This is obviously now taking into consideration that it is not only the arrowhead, but it is also the diamond that has 1, 2, 3 vertices at the circumference, and one of them is at the center. When we have that diamond, the arc BC subtends an angle at the center. The same arc BC subtends angle A at the circumference. Therefore, angle at the center is 2 times the angle at the circumference. So when we say X is equal to 2 times 80 degrees and we get 160, you must understand that the reason is very clear. Angle at center is equal to 2 times angle at circumference. Okay. Anatima said is asking what will angle P and C be equal to. We're not given any information, Anati, so we can't say. We can't say what angle P and angle C will be for this particular diagram. They would have to give us more information. Angle P and C, for it, by the way, let me just say it from the get-go, is not opposite angles of a cyclic quad, because PNCO is not a cyclic quad. Why is P, N, C, and O not a cyclic quad? Because remember, a cyclic quad has all the vertices on the circumference. A quad means a 4-sided shape, so that means all the vertices of that particular quadrilateral need to be on the circumference of the circle. Here we are one shy. O is not at the circumference, therefore we cannot use the cyclic quad theorems to be able to say anything about P and C. So what I'm saying is that this is just an example where I'm trying to just do what? Emphasize the point of angles at the center being twice the angle at the circumference. And what we use there is that for our arrowhead, our diamond, and our bow tie, we can see that 1, 2, 3 points, vertices, are at the circumference of the circle. One is at the center deliberately because it speaks to the theorem of angle at the center is twice the angle at the circumference. Let's come here to this last diagram, because I see some of you feel like you're a bit out of your depth when it comes to this diagram. Let me just redraw this bow tie, maybe on a diagram that's a bit bigger. Okay, so that you can see what I'm talking about. Here is the bow tie. Okay, maybe now it's a bit bigger. Let's say you had O, you had A, you had B, you had C. This A, just forgive me there, just please take it that this A is exactly at the circumference of the circle. B is exactly at the circumference of the circle. C is exactly at the circumference of the circle. Okay, so which angle is at the center? Arc AB is the only arc which subtends an angle at the center. Look at arc BC. Arc BC is subtending an angle here. It's not at the center. Arc CA, all right? You could say maybe arc CA is subtend, but the thing is, really and truly, it's not really helping much, because arc CA does not then subtend any other specific angle, arc CA, at the circumference. Does that make sense? So basically, arc CA is out. Okay, arc AB is the only one that is in the game. Look at this. A, B, they both pointing towards this angle. Angle at the center is that one. The same arc AB, look at it. You see this? Look at that AB. We go here to see angle at the circumference. Yeah. So if I am given that this is 50 degrees, and I'm asked what the value of x is. It seems like I love 50. Let's change it up a bit here. Let's say 80. Okay, let's say I'm given that this is 80 degrees. Then what will x be? Okay, and what would be our reason? Okay, I want to change it to 80 because I love 50 and 50 is getting the best of me. We used 50 there. Let's change it up now and use 80 degrees. Okay, what would angle x be? Okay, you guys get the point, right? X would be 40. Okay, and we don't forget to write our reason. X is equal to 40 degrees. Reason, angle at center is equal to 2 times angle at circumference. That is the center theorem, guys. That is the center theorem. Okay, so I beg you guys, 3 diagrams. Okay, we divide the angle at the center by 2. Yes, we do that because, as the theorem says, angle at the center is twice the angle at the circumference. Okay, so when we divide this one by 2, we get 40. And that 40, since they are saying angle at the center, that angle at the center is twice. What's 2 times? 2 times what will give us 80? It's 2 times 40. So x has to be 40. Okay? Yeah, x has to be 40. Yeah, guys, please don't rush me. For instance, I can see Anati Maseti is like, how is it different? I need you first, Anati, to lock in and be sure about angle at the center with the arrowhead, angle at the center with shine bright like a diamond, angle at the center with our bow tie. Take note, circumference. There's 3 of us on the circumference, but 1 of us is at the center. And that's how it should be with angle at the center is twice the angle at the circumference. With the bow tie, 3 of us are at the circumference. 1 of us is at the center. With the arrowhead, 3 of us are at the circumference. 1 of us is at the center. With the shine bright like a diamond, 3 of us are at the circumference. 1 of us is at the center. Okay? Okay, does that make sense? Yeah. Flavorful sense. Yes, sir. I understand. I wanted to pass it to someone who might still be confused. No, that's good. I'm happy. Pass it on. Knowledge when it is passed on is better than knowledge that is kept for selfish purposes. Because if you keep the knowledge for selfish purposes and you think, yeah, now I finally found the secret once and for all, and then you want to nurture it and not share it with others, you are going to forget it as soon as you start thinking in that way. So the key then is to find someone who is probably, you feel like they are in a worse off position, and then you still go and share it with others. Shofstar speed, you are saying you are still confused. What are you still confused about? Yeah, guys. You see, the thing is, I've been explaining that theorem over and over again. So if someone is still confused, even after revisiting it over and over again, all right, I don't know. Then I think that means I unfortunately, it unfortunately means that maybe you need to find someone who can explain it more simply. Yeah. All right. Because you guys have been explaining this thing. It's like I feel like I've been going around in circles with that theorem. Going around in circles for the purpose of like people finally getting it. So if after many times going around in circles you are still lost, you need to let me know where are you lost? The bow tie. We were there just now, Jay. We were there just now. Lost the angle which an arc of a circle subtends. The angle which an arc of a circle subtends. So come here to the bow tie. My question to you, which arc is subtending an angle at the center? Here we have it. We have arc AB, we have arc BC, we have arc CA. You must tell me which arc subtends an angle at the center. Shorter speed. You need to answer now because you are the one most at saying you are lost. You are lost like nobody's business. Learners like you in my class, I usually bring them to the front and they stand there, and I make them stand, and I explain to them until they can tell me that they are fine. Shorter speed, AB. Are you sure it's AB? And you're not just being what you might call you're not just falling into peer pressure. You are saying AB because everybody is saying AB in the comment section. Hello.
No, say hello, sir. Shh. Hello, sir.
Hi. Oh man.
Yeah, sir, like yeah, get AB, sir.
Are you sure it's AB? You're not falling into peer pressure.
No.
Oh, okay. So
I'm
you're
sure.
sure it's AB. You are sure it's AB. Now come with me.
Yeah.
Since you said it's AB, let's go and read the theorem statement. The theorem statement says the angle which an arc of a circle subtends at the center of the circle. So I like what somebody said in the comment section. Respect RSP is like saying, let me ask you, why are you saying it's AB?
Because I get it AB, it subtends. Yeah, subtends from go omu.
Okay, so you are right. You are correct, right? AB, arc AB is the only arc that subtends the angle at the center, and you can see that it does. So you can see, for instance, from A and from B, as you move towards, leading by these sides OA and AB, you can see that from AO and OB are leading us directly to angle what? To angle O, which is the angle at the center. So it can't be BC because look at BC where it goes, right? It goes here. That's not the center. It can't be AC, arc AC, because arc AC, I mean, you can see, man, I mean, Arc AC.
Yeah.
So it is only arc AB. So the theorem says that the arc subtends an angle at the center. So the angle that the arc subtends at the center will be twice the angle that is subtended by the same arc at the circumference. Now look at AB. It not only moves along OA and AB to O, but it also moves with AC and BC towards who? C. Ne?
C. Yes, okay.
Yes. So these are the two angles we are talking about. This angle here will be twice the angle here, which is at the circumference. Why?
Okay.
Because these two angles are both subtended by arc AB.
AB.
Mm.
Okay.
Okay. Are you sure?
Yeah, say.
No peer pressure.
Okay.
Okay.
No
That's
peer
fine.
pressure, say.
Sorry?
Okay.
You are fine.
Yes. Thank you, say.
Okay. Okay, sure, then. That's no problem. Okay. I'm glad you are good. Okay, so I was beginning to think there that maybe Clockster must find some other person to, walk her through so that she can have clarity. Because so that's center, guys. Center. All right. Now I'm going to do one last theorem that has to do with something that has to do with center. Because the reason that I'm just focusing on center is so that we can just have a primary focus on the center. Okay, because oftentimes in your geometry problems, even your complex problems, the problem with learners is not that other problems are difficult. The only reason why they are difficult is because we can't see our close friend amongst the other 1,000 students at school. But the minute we can identify our friend because we know our friend very well, then it's easy. So it's like the theorems. Each individual theorem is like a friend. You must know each individual theorem, the diagram, how it looks like very well, so that the minute you see something, then you're like, oh, okay, that one is angle at the center. Oh, okay, that one is that. You see? I hope it makes sense. So please, guys, please. Yeah. The last one that has to do with center is this guy. Very famous, this one. Very famous, this one. Okay. I can see in the comment section already someone has tattered it already, jumping in and tattering the thing on Tatil. Okay. There. Okay. What do we call AB? The line AB is called a what, guys? What is the line AB called? Okay. Yes, flavorful sense. Yes, butylamiine and molimo. It's the diameter. AB, guys, is the diameter. All right. So the theorem says the following: the angle subtended. You see this word, subtended. Okay. Subtended at the circumference of the circle by a diameter is a right angle. The angle subtended at the circumference of the what? Of the circle by a what? By a diameter is a what? Is a right angle. Okay. So that means then AOB, if AOB is a diameter, And then we can see the following: a closed triangle subtended by that diameter for the closed triangle. That means angle C should be equal to what? Right angle, guys, means 90 degrees. So you don't see in the diagram the 90. What you see is a diameter, because the condition is that the angle subtended at the circumference of a what? Of a circle by a diameter. I want to add, guys, that this needs to be a diameter that basically leads to a closed triangle. It needs to lead to a closed triangle for the angle that is subtended by that diameter. Okay, I know this, they don't say anything about, oh, closed triangle, but let me tell you this, guys. It has to be a closed triangle, and that triangle has to be drawn from the end point of the diameter to the other end point of the diameter. Listen to me when I say that. Closed triangle drawn with its sides from the end points of the diameter. If it's not drawn from the end points of the diameter, then that angle, whatever it is not 90 at the circumference. Closed triangle from the ends of the diameter, then that angle is going to be 90. Because, guys, they are not saying a part of the diameter subtends 90 degrees at the circumference. No, they are saying the entire diameter from the end points of the diameter, it must be a closed triangle that basically leads to the 90. Okay, BTK, this is a closed triangle. Okay, look at this triangle ABC. The B is the end point, the A is the end point, and the triangle is basically closed. Points B, C, A. Then we can comfortably say angle C is equal to 90 degrees. What's our reason? Angles in semicircle. Yeah. I love lab. If there's no closure, then you can't talk about 90 degrees at the circumference. You can't. You can't. All right. Yeah. The theorem. You see, in a theorem, there are things that are basically implicit. They are not explicit. All right. Okay. There are things that are implied. They are implied in the statement. So when they say the angle subtended at the circumference, I repeat, the angle subtended at the circumference of the circle. Of course, guys, there won't be an angle at the circumference unless, okay, there's a line extending from the what? There are lines extending from the diameter. But I'm saying these lines that are extending from the diameter, let me just show you what I mean. Let's say we had a triangle like this. Key diameter, key O, key A, key B, right? And let's just say there was a triangle here, and let's say it was C. Okay. Okay. If let's say this was C1, this angle, what I am saying to you guys is that you cannot say that angle C1 is 90 degrees. Do you understand what I'm saying? Why can't you say angle C1 is 90 degrees? The reason is, do you see this line? And do you see this line? This is basically the lines that join the vertex there to form this angle. But these lines are not coming from the end points of the diameter, which is the end points of the diameter on the circumference. They are not coming from there. So we can't say angle C1. So one cannot say, oh, is a diameter. Diameter subtends 90 degrees at the circumference. In other words, angle C1 is 90. We can't say angle C1 is 90 degrees. This is what I'm trying to say. All right. The triangle needs to be formed from the end points of the diameter. In other words, it has to be from here to there. The line here with the closed triangle. So the only 90 degrees that we have is for angle C, is for angle ACB, not angle C1. The only 90 that exists is for angle ACB, because that is the triangle firstly that is closed, which is formed from the end points of the diameter. The triangle is formed from the end points of the diameter. These are the key things. So your triangle must be formed from the end points of your diameter. That's one. And it must be closed. Okay, that is true angles in a semicircle. Guys, if that is sorted, then you are good. You are sorted. Okay. All right. I hope you are hearing me, people. Okay. Am I being heard? Am I being understood? Am I audible to you in what I am saying? All right. BTK 4K. I feel like BTK 4K, you've basically not been hearing me from the get-go. And unfortunately, my guy, as I have been saying in the live, if you can't hear me, then I think please make it a point to go to someone until you understand it. All right. I don't claim when I come here to be able to explain, in a way that will be palatable or appeasing to everyone. I don't claim that, guys. Me, I know I have my own flaws and foibles, but at the end of the day, you must go and always find out and figure it out so that you don't get lost. Okay. Oh, it's raining that side. Ish, that's a pit. So network issues, they are doing the things. I askis, my guy, askis. Anati Maseti, let me show you something. Anati asked something earlier on about bow tie. Let me show you something, Anati. There's a difference between the bow tie. There's a difference between this bow tie and obviously then, as you have seen, this bow tie. There's a difference between this bow tie and this bow tie. Okay. You can see what's this bow tie. 1, 2, 3. 3 of these vertices at the circumference. 1 we would obviously take being at the center. So that this one is for angle at the center is twice the angle at the circumference. The arc subtending angle at the center. The arc subtending the same as another angle at the circumference. This bow tie is for angles in the same segment, in other words. Okay, here this angle is equal to that angle. That angle is equal to that angle. Right? So I know you were asking earlier on. Okay, I'm just addressing you because I could see you were asking deliberately now to find out what is the difference. This bow tie is for angle at the center. Okay, is 2 times the angle at its circumference. So here we are talking about the angle at the center, the one that is subtended by the arc, and the same arc subtends this angle at the circumference. Okay. Then here specifically, angles in the same segment. Okay. I hope you understand. So this one, you can see how many points are at the circumference. 1, 2, 3, 4. And remember, what did we say about 4 points at the circumference of the circle? This means that this is a cyclic quad. It's a true cyclic quad. 1, 2, 3, 4 at the circumference of the circle. In fact, angles in the same segment implies that, of course, that is a cyclic quad. Concyclic, very good on Tatile, remembering that important critical word being used. Okay, no guys, I was just trying to sort out and resolve Miss Mercedes question. You do. I'm glad you do. You should, and you should never forget it. So what Sir is going to do now is going to hold it right there on the center theorems. I don't want to rush. I don't want to rush through. So for today, guys, I covered the basic aspects. Okay, I had people come into the live and I saw them comment and say, what is the arc? It means that they missed the beginning of the lesson. You know, we first defined what a circle is, and then we went through, if you were actually good at maths, what would you teach? Are you kidding me, Aline? Like, what am I teaching, Gandhi? What is it? If I was actually good? Who is this guy now? We don't need this KAK. Man, some of you guys are beautiful people. You know, I like how honest this user is lost in love. This user is lost in love. There's someone who is called this user is lost in love, and he just commented. Guys, look at this beautiful language. Look at this. This is what, okay, I think my thing doesn't want to pin it. We don't need this KAK. It's just a bit unfortunate. I wonder what is he going through right now. Because I usually, it's funny because sometimes when people comment, I like see, it's almost as if I kind of sense what it is. It's a born frustration. There's a frustration that is within that they are taking out on the live. I hope whatever you are going through, you can be able to get over it, my dear, and you'll be fine, right? You are more than welcome to DM me, if you need like anything. Just don't. Yeah, it saddens me when people just. Yeah. But anyways, man. Okay, so these were the notes that we looked at the beginning, where we were defining various things. If you guys remember very well, at the very beginning of the lesson, I defined what a circle is. We defined, what a center is, definition of a center, what a center is, what a diameter is, what a circumference is, what a radius is, what a major segment is, what a minor segment is. Remember this we called a sector, but a major segment is the bigger, because a chord divides our circle into segments. So this here in orange, the orange area we call the minor segment. Then the bigger region we call the major segment. I love lab. What did you ask? Don't even know what you asked. Sorry, my bad. Missed your question. You asked a question. What is the question? What time do you usually start your lives for grade 11? This was... Remember, guys, I gravitated towards grade 11 after having completed some of the basic things that were with regards to all the other grades, grade 8 and 9. But I said these live lessons are for all grades. Today, I started with circle theorem, so I had to specify that it's for grade 11, so that people don't stay here if they are in other grades like grade 8 and 9, but this won't be relevant to them, until like a few years, forward. Remember, this is relevant to grade 11, but anyone who wants to learn can stay here and learn and gain the knowledge. All right, because it's for you at the end of the day. You empower yourself most. So sector arc, 9 p.m. is when I start. Okay, if it's a good opportunity to start, I start at 9 p.m. guys, and that's really truly if the opportunity does avail itself. 9 p.m. I just answered you 9 p.m. But what time? 9 p.m. Okay, arc, okay, tangent, we defined what a tangent is, cyclic chord, we defined what a cyclic chord is, secant, what a secant is, okay. Then also we looked at the first theorem with regards to center, okay, which basically in summary says if a line is drawn from the center, okay, a line drawn from the center of the circle perpendicular to the chord, what does it do? It bisects the chord. So our statement for this diagram, we can say AM is equal to MB, and our reason is line from center perpendicular to chord. We looked at the opposite or the converse of this theorem, which says a line segment joining the center. In other words, a line from the center to the midpoint. What does it do? It is actually perpendicular to that chord. So we can, for our statement with a diagram like this, say OM is perpendicular to AB, which is something we don't see. Our reason, on the other hand, is what we see, the line from center to the midpoint of the chord. So those were the two center theorems we started off with, all right? And we were very specific and direct about the statement and the fact that sometimes, remember, these questions that get asked in geometry is where you have to fill in the missing word. We need to know our theorems off by heart so that in any event, when they ask us to fill in a missing word in a given theorem, we can actually do so. Then we looked at the angle at the center theorems. Remember the angle at the center theorems? We looked at three diagrams, the arrowhead, the diamond, and the bow tie. Remember, these, all three of them will have vertices at the circumference. Okay, all three of them will have vertices at the circumference, remember, and don't forget that. Okay, let me try and also remove the comment section just for a little while so that people can screenshot. Well, you guys can remove the comment section on your own, right? I think it's possible. You guys can do that from your side. You just flip, you just switch mouse. Okay, I think it's possible to do that. Okay, so I'm going to raise this so that you can see it, and then I'm going to move back to the previous side so that I can raise it so you can see what I did there. Okay, so this is one side. All right, this just was like us trying to get through the basics there. Okay, this was the first page. Let's get that up raised so that you guys can see. Hope you can see clearly there. I'm sorry, I can't see what you guys are saying, so I won't know what you're saying. But if you want to say something, maybe you can guest request and then you can say it so I can hear you. Like, have the confidence, like Clockster Speedy. I think Clockster Speedy is gonna be the next I Show Speed because she's got Speedy in her name. All right, okay. And then that was the last back page with angle subtended at the circumference of the circle by a diameter is a right angle. The angle subtended at the circumference of a circle by a diameter is a right angle triangle. Then I explained specifically that the triangle that they are talking about for that diameter has to be a closed triangle, but it has to also be formed from the end points of the diameter, not from anywhere else, because the 90 degrees formed can't be true if it's formed from anywhere else but the endpoints. Then I also explained the difference between the bow tie of angle at the center is 2 times the angle at the circumference, and the bow tie of angles in the same segment. They're not the same. Okay. Yeah, take note of these things, guys. This is what makes a difference for a learner who is doing geometry when they understand the little stuff, the little things that make a world of a difference in your understanding. It elevates your confidence. It makes you, feel like, yeah. And when you have that yeah feeling when you do geometry, then, it's nice, guys. Geometry can be so nice and easy. Okay. I'll tell you this, that in some of the schools that I'm having the chance to really work at, like, you're actually finding that our learners are finding geometry to be more easier than even paper 1 and some of the paper 1 aspects, because we've kind of made the geometry become a bit more accessible than it originally was, and it's becoming easy for learners to actually answer geometry problems more and more as the years go by. So yeah, let's get on to that bandwagon and start having that sort of like positive confidence and mindset when it comes to geometry. And when we do, LG, guys, life's good. LG, life's good. Okay. Right, let's see if we can't find the some questions. Okay, let's look at some questions and just see if, yeah, look at this. Pull up Glen Austin High. BTK is like pull up in Glen Austin High. Yeah, you get a heartbreak there. What's happening in Glen Austin High? Where is that? Where is that? Which province is that? In the diagram below, a circle centered at O. So diagram below, a circle centered at O is drawn. Okay, here's the circle centered at O. It's drawn. You have H, J, G, and L. H, J, G, and L. And it says they are points on the circle, right? Triangle H, L, H, J, L. Oh, Gauteng Midrand. Oh, okay. I hear you. Hala. HJL. Triangle HJL is drawn. Here is triangle HJL is drawn. HOG. HOG. What does it do? Bisects. This word, guys, bisects. HOG bisects who? JL. Who is JL? That is JL. And you can see this word bisect. Already we can see that JM is marked as being equal to ML. Okay. O is the center. Okay. So this line is coming from H through the center to G. Does that make sense? All right. HOG bisects JL. HOG bisects JL at M. HJ. HJ is 12 root 5 units. And JM is 12 units. What do they want? If MG is equal to 6 units and OM is equal to X, write HM in terms of X. All right. Do we see what this question basically they are putting to us? Okay. So let's look at the statement one more time. In the diagram below, a circle centered at O is drawn. Circle centered at O. So once again, we see the keyword centered at O. So the minute we hear center, many theorems must come to mind, like the ones that we did. Okay, the one center theorem that we looked at was this one. Okay, line from center perpendicular to the chord bisects the chord. So from this one we can say AM is equal to MB. There is our acceptable reason, line from center perpendicular to chord. There's this one, line segment joining the center of the circle to the midpoint of the chord is perpendicular to the chord. So we have that circle, right? Line to the midpoint. Okay. Then we have our 3 diagrams. Okay. Arrowhead, Mr. Bowtie, Mr. Diamond. Okay. And we all know that arc AC, that angle is the one at the center. This one is the one at the circumference subtended by arc AC. Okay, so we have those theorems that basically we have just touched on, which are still fresh in our minds, and we can use them, you know, for the purpose of answering questions. Then we have, obviously, the angle subtended at the circle by the diameter is a right angle triangle. And we spoke about the specifics where this is concerned. Okay, if AB is the diameter, we can say that the angle there that is subtended, as long as the triangle is formed from the end points of the diameter, then we can say the angle is 90 degrees. So given that information, all of that info, okay, the minute we say in diagram below a circle centered at O is drawn, okay, we know that the center, we know that the line drawn from the center, this here, we are told furthermore that HJG, JG, and L are points on the circle. These are points on the circumference of the circle. Triangle HJL is drawn. Okay. HOG, what does HOG do? It bisects what? JL. HOG bisects JL. At who? At M. HJ is 12√5 units and JM is 12 units. Now, let's come here. If MG is equal to 6 and OM is equal to X, write HM in terms of X. Okay, so I'm sure you guys know what the length of OM is. Okay, OM is X. That is from here to there. OM is X. Okay, are we good with the fact that OM is X? Because that's what's given to us. MG is 6. This is the length of the radius from G to O. That is our radius. Okay. But now we are being asked to calculate the length of HM. But of course, we know that HO is equal to OG. Why is HO equal to OG? These are both radii. And we know our radii are equal, right? HO is a radius. OG is also a radius. The two are equal. Okay. We already know that OG is equal to X plus M. That's what OG is. OG is equal to X plus M. Therefore, HO is also then equal to X. No, OG is equal to X plus 6, not X plus M. X plus 6. OG is X plus the 6. So then HO is also equal to X plus 6. So OM is equal to X, that is given. We then know that HO plus OM is what will give us HM. HO plus OM is what will give us HM. What is HO? X plus 6. What is OM? X. That will give us HM. We add these two. X plus X is 2X. 2X plus 6 gives us HM. So therefore we can say HM is equal to 2X plus 6. So let me go back again so that you guys can understand what I just did. This HG, we can all agree, is a diameter. HG is a diameter. That we can see. Why can we say HG is a diameter? We were told that it passes through in the diagram below, a circle centered at O is drawn. Now, if this is a center, then H all the way to G is a diameter. Furthermore, HO we said is equal to OG. Why is that so? It's because radii, we say radii are equal. That's why HO is equal to OG. Our radius are equal. Then, to determine OG, we can find OG because OG is going to be this OM plus this MG. What's OM? OM is X. What is MG? It is 6. So that means OG is X plus 6. I'm done with OG. But because I had said HO is equal to OG, it means if OG is X plus 6, then HO is also equal to X plus 6. Now furthermore, since HO is equal to X plus 6, I know OM is equal to X. OM is equal to X. So since that is the case, the entire HM will be equal to HO plus OM. HO I already know is X plus 6. So we add it to OM, which is X. Then we add the like terms. X plus X is 2X plus the 6, which means HM is equal to 2X plus 6. That is HM in terms of X. They said they want the right HM in terms. When they say in terms of X, one of the terms in the expression for HM should have the variable X. That's what they mean. So we're able to figure out what the length of HM is. And guys, to be honest, whenever I find things, I update them in my diagram. HO, for instance, I found that it is X plus 6, so the HO is X plus 6. OM is X, MG is 6. So that's updated information. And of course, the entire HM, this side of the triangle HMJ, this whole entire length is going to be 2X plus 6. So I would actually put that in there as 2X plus 6 so that it can help me at any other point when I need it. Let's look at number 1.2. Hence or otherwise giving reasons, the length of the radius of the circle. So they want the length of the radius of the circle. In other words, they want the length of HO. They want the length of HO, the actual length of HO. Now this will be very interesting, but I think we can definitely do it. Okay, we can definitely do it with the information that is given. We can look at that diagram, and in that diagram we can see that triangle HJM in triangle HJM. There's a few things that we can do there. We can say HM is perpendicular to JM. HM is perpendicular to JM. Why, guys, do we say HM is perpendicular to JM? Why? I want to ask that question. Why can we say HM is perpendicular to JM? Because let me just give you an idea into my trail of thinking. I can see that this triangle HJM already has JM, which is 12 units, and JH, which is 12 root 5. And already I have the length of HM, but it is in terms of X. So if I can then use Pythagoras theorem in this right angle triangle and find the value of X, then I can take that value of X, substitute it into the length of who? I can substitute it into the length of HO, which is X plus 6, which is the expression of the radius. And substituting that x value plus 6 will give me the actual length of the radius of this circle, because HO is a representation of the radius of the circle. Okay, I hope that's clear now. Or I could use OM, which is also x plus 6. After finding the value of x, I can substitute it and get the value of HM. So you guys have 100% answered. Some of you have said the reason why we can say HM, the reason why we can say HM is perpendicular to JL is because of line from center to midpoint of chord. I want to send you back to my acceptable reason. Line from center to midpoint of chord. Just want to send you back to my acceptable reason. Line from center to midpoint of chord. OM is perpendicular to AB. OM is perpendicular to AB. I write what I don't see. What's the reason? Line from center to midpoint of chord. So those that said line from center to midpoint of chord, 100%. 130, the line from center to midpoint of chord. When I say HM is perpendicular to JM, I am in other words saying that is 90 as well as that is 90. That is encapsulated in HM being perpendicular to JM. Then in that triangle, I'm not going to use Pythagoras. I'm going to say HJ. Take the square of the hypotenuse side. HJ. I'm going to take HJ and square it. And the square of the hypotenuse side is equal to the sum of the square of the other two sides. So I'm going to say JM squared plus HM squared. Then I write the reason, guys, because in geometry we write the reasons, and in the acceptable way, Pythagoras. Then I can substitute in the place of HJ 12 root 5 the whole thing squared. That is the hypotenuse. JM 12 squared. HM 2x plus 6 the whole thing squared. Now this is going to have an equation where I'll be able to solve for x. So 12 root 5, that's 144 times 5, which is equal to 144 plus, what's 2x plus 6 the whole thing squared? Remember, I opened two brackets of 2x plus 6 so that I don't forget that I'm supposed to FOIL. Okay, so my algebra is coming back. What's 144 times 5? Help me out there, guys, in the comment section. I don't have a calculator. And 44 times 5, my beautiful people, my beautiful peeps. Thank you, Charlotte Doreen. Charlotte Doreen, you're back. Molimo, thank you. 720, guys, 720. Thank you. Is equal to 144 plus, so that's 4x squared plus 24x plus 36. Just cutting straight to the point, guys. Why am I saying 2x times 2x is 4x squared? 2x times 6 is 12x. Another 2x times 6 is another 12x. 12x plus 12x gives me 24x. Then 6 times 6 is 36. Now I'm just going to write the equation in standard form. 4x squared plus 24x plus 36 minus 720 plus 144. And my pen is dying a slow death. You kid me. Pen is dying a slow death. 36 minus 720 plus 144. See all these live lessons. Stationary is disappearing here. Eh? What's 36 minus 720? Let's grab this. See, I just wanted you guys to do the work for me. Minus 720 plus 144 minus 540. Then get x squared plus 6x minus 135. X squared plus 6x. What did we just do here? We divided each term by 4. Got x squared plus 6x. X squared plus 6x. Right? Then you factorize, thinking of the factors of negative 135, which when we add, we get 6. When we multiply, we get negative 135. So that means the factors are not going to be having the same sign, but the highest factor will be positive. What are the factors of 135? Which when we multiply give us 135, that's negative, but when we add them we get positive 6. I already know what the factors are. Let me just see if you guys know. What would you say are the factors that do that? Right, now that is not to say if you feel like you want to use the quadratic formula, you can't. You can definitely go ahead and use the quadratic formula if you feel like it's going to waste a lot of your time trying to figure out which factors when multiplied give you negative 135, but when you add them give you 6. Okay, I already know what the factors are, but I want to check if you guys know as well. Factors of 135. Come on, guys, come on. I believe in you. The one who made the dead is moving it. What? Are you guys struggling to find the factors? Okay. Charlotte Doreen. I wanna see Charlotte. And me, Charlotte. I wanna learn Charlotte. I wanna learn Charlotte. I need to be alone now. Right now, right here with you. Hi, Charlotte. Okay, Charlotte, thank you so much. Eh? Yes, it's positive 15 and negative 9. Okay, very good. Positive 15 and negative 9. 15 minus 9 gives you 6. 15 times negative 9 gives you negative 135. Then we simply say x is equal to negative 15 or x is equal to 9. Now, if we were to be honest, which number would fit the description of what we actually want for the triangle? If x is a negative value, negative 15 plus 6 will give us negative side lengths, and we can't, and we don't, and we shouldn't have negative side lengths. So we are going to say x cannot be negative 15. X is equal to 9. Okay. Now remember, what did they ask for initially? They wanted, hence or otherwise giving reasons, the length of the radius of the circle. Expression of the radius, HO, is x plus 6, as well as OG, which is the radius, is x plus 6. So I'm just going to say OG, okay, is equal to x plus 6. 9 plus 6. 9 plus 6 is 15. 15 what? Units. That's OG. Therefore, you just say the radius of the circle is 15 units. Okay. World of a difference. Okay. World of a difference. Okay. Guys, I'm gonna cap it right there. We will do more exercises on circle type center theorem questions, and then we'll move on to the next type of theorem questions, the next family. From the centers, we could establish what it is that basically we need to look for when it comes to centers. Center, there's your radius. As you can see, guys, there's other things that we can really take into consideration when we deal with this. So tomorrow I will continue with more. We'll look at more center type questions, all right? Just like a little bit more with a little bit mix of exam type as well. Yeah, just so that we can iron out these theorems. But that's not stopping you from actually going and thumping through some questions that have to do with center or circle theorems and practicing, so that you can actually get your groove back on with geometry. It's important to get your groove back on. Geometry is not difficult, very nice and easy, but it just needs, you know, not giving up, a lot of tenacity and some staying power. But thank you so much, guys, for those that joined. I love all of you. You really are near, dear, and special, because you guys have made yourselves part of my live lessons. Some of you have been rejoining. You guys are not sick of me yet. Trust me, you will at some point, and this voice will become very agitating to you and your soul. But thank you so much for joining. Dear Shlochsla Speedy, it was great hearing your voice. It was good to have that short minor interaction, and I'm glad that you are vulnerable enough to sort of like say in the comment section when you don't understand something. If we didn't have that interaction, maybe, just maybe, you would still be lost about Mr. Bowtie. When it comes to angle at the center is twice the angle at the circumference. Shine bright like a diamond. I think you guys understand shine bright like a diamond. With angle at the center is twice the angle at the circumference. And obviously our arrowhead, you know, that's also something we need to make sure that we understand well. So understanding the theorems, understanding the statements, and knowing those off by heart will really put you at a very safe place. Thank you, Doreen. I want to see Charlotte. You don't need Charlotte. Charlotte. I need to be alone now. Yeah, Charlotte. Okay, thank you so much, guys. Have a good one. We'll see you on the flip side again when days are better and sweeter. Cheerio, and please practice, guys. Just practice. Don't necessarily wait for the live, and you can learn everything on your own, you know. Just come here to kind of make sure you are recapping and understanding what you really thought you understood. Okay. Okay, bye. Nine, guys, nine. If I come on earlier, if I come on during the day earlier, then you must know that it's just that time has availed itself. But